In our second tutorial, we will be able to prove that two functions are inverses using composition. So let's flip over our notes to this section, and we're going to learn how to prove that functions are inverses. So in order to do this, we must show that each composition, meaning f of g of x and g of f of x, both of those compositions must be equal to x. They must be equal to x. So here's our direction. Let's determine by using compositions. There are other ways to do this, but right now we're going to learn by compositions. Determine if f of x and g of x are inverses. And of course, we're going to show our work to justify our solution. So if we're going to prove that f and g are inverses, we need to first look at f of g of x, and then we will look at g of f of x. And if both of those compositions equal x, then we have proven that they are inverses. So here's our f of x and here's our g of x. The first thing we're going to look at, let's look at f of g of x. We got to do both of them, so we might as well start with this one. F of g of x. This is a composition. We're picking up the entire g of x function, and we're going to plug it into the f function. So let's start inside and work out. Inside means that's the g of x function, and here it is, 1/2 x plus 3. So actually what I'm going to do is I'm sort of just going to cross out the g of x symbol, and let's just put in 1/2 x plus 3, because that's what it is. Ultimately, I'm talking about f of 1/2 x plus 3. I'm looking at that. So f of 1/2 x plus 3 means I'm going to plug that 1/2 x plus 3 right into the f function right here. So I'm going to have 2 times the 1/2 x plus 3 and then minus 6. So there's my composition. You can see the major f function here, 2 times something minus 6. 2 times something minus 6. It just happens to be that this something this time is the entire g of x function. That's f of g of x. And if these are functions, this will all cancel down to become x. So let's see what happens. We're going to distribute. We'll do 2 times 1/2 x. 2 times 1/2, of course, is 1, so this becomes 1x. 2 times 3 becomes 6, and then we have this minus 6. So you can see that the 2 and the 1/2 cancel out, and now we can see that the 6 and the negative 6 cancel out, and look at that, we get x. I'm going to put a little check mark because half of our problem has worked. We're not finished. We did f of g of x. Now over here, let's do g of f of x. We have to do both compositions. Okay, so very similar. I'm going to scratch out this f of x, and I'm going to put 2x minus 6 in its place. Here's the 2x minus 6. So we're really looking at g of 2x minus 6. That means the 2x minus 6, we're going to pick it up, and we're going to plug it right in here to the g function, right in place of this x. So the 1/2 is here. The x now has a new name. It's this entire 2x minus 6. And then the plus 3. Don't forget that last part. This is g of f of x. You can see the g function, and you can see the little f of x function inside of it. And now we're just going to do some quick algebra. We're going to distribute again. 1/2 times 2x. Again, the 1/2 and the 2 cancel each other out to get a 1. So 1x. And then 1/2 times negative 6 is negative 3. And then, of course, you can see that those two things cancel out. And we also get x. Since both compositions equaled x, yes, these are inverses. I'll put an exclamation point because I'm excited about that. Notice that the direction says determine. Determine if they are. That doesn't say that they must be. It says, will they be? Yes or no. So we showed our work and we proved that yes, these are inverses. Let's look at example 6, the next example. Two new functions, still f of x and g of x, and I want to see if they are inverses. So the first thing I'm going to look at is f of g of x. We'll start there. F of g of x, okay. So I'm going to kind of scratch out the g of x. G of x is right here, x plus 4, so I'm going to put that right in here, x plus 4. So I'm looking for f of x plus 4, which means I'm going to pick up this x plus 4, and it's going to go right in here for this x. So let's read my function. I have a 4 and then a minus sign. So here's a 4 and then a minus sign. And then x is being replaced by x plus 4. Well, if I'm replacing a monomial with a binomial, I better put that binomial in parentheses because I'll be subtracting both parts of it. And now let's see what happens. So I'm going to distribute, it's like a negative 1 here, subtracting x and subtracting 4. So of course I have a 4 here. And then minus x, and then minus 4. So I can see that 4 and negative 4 cancel away, but I'm still left with negative x. Look at that. That's not what we're supposed to get. I might go back and double check my work to make sure that I've done things correctly, but I'm pretty confident in my work. Since this did not equal x, these are not inverses. I don't even need to look at the other composition. If one of them does not work, then they are not inverses. Now, again, I might go back and check my work to see if I messed something up, but I didn't. They're not inverses. Let's look at our final one. A new f of x and a new g of x. Let's do f of x first. Excuse me, f of g of x. So I'm going to replace the g of x with, at least that symbol, with what it is. It's quantity x plus 3 cubed. So we're talking about f of x plus 3 cubed. Got a bunch of parentheses here. So we're putting this x plus 3 cubed right in here in place of this x. The only thing that's changing is the x. The cube root is still there, the minus sign, and the 3 is still there. So we still have the cube root. I'm putting this x plus 3 quantity cubed underneath it in place of the x, and then we have minus 3. Minus 3. Let's see what happens here. So I have a quantity cubed, and it's underneath a cube root. Well, that makes sense that these cancel away. And then I'm left with x plus 3. It doesn't really need to be in parentheses because it's really just a 1 in front of it. So it's really just x plus 3 and then minus 3. And we can see that those two will cancel away, and we're left with x. Yay! We're halfway to proving that these are indeed inverses. But we're not finished. We do need to find the other composition, g of f of x in this case. So I'm going to scratch out the f of x, and let's put the f of x in place of that. This is the cube root of x minus 3. So the cube root of x minus 3. So g of the cube root of x minus 3. So that means this whole g of x function is going to go right here. So I start off with the parenthesis, and then my new x, which is all of this stuff. So cube root of x minus 3, and then a plus sign, and then a 3, and then a parenthesis, and then a cube. The only thing that changed was this x. Now, yeah, sure, probably I should have put this in parentheses, but it's really just a 1x right there, so it doesn't really need to be in parentheses. In fact, I'm just going to take those parentheses away right now. The main parentheses are right here. We'll deal with that in a minute, but this is just the cube root. It's like 1 times this stuff, so that's the cube root of x minus 3 plus 3. Now be careful which things you cancel out first. I know that a lot of you see that this is being cubed, and this is a cube root, and a cube of a cube root will cancel out, but don't forget you still have these things. These things actually cancel out first, a negative 3 and a positive 3. They have to cancel out first, and then we can take our cube root and undo it with the cube. Cubing a cube root cancels out, and hey, look at that, it's x. So once again, yes, these are inverses. And that's it. That's how you prove if two functions will be inverses. You find their compositions and you make sure both of them equal to x. Now let's talk one last thing about why we have to be equal to x. If you remember back when we were looking at inverses graphically, let me just draw a quick graph. When we looked at inverses graphically, for example, let's say we had this parabola here, and its inverse looked, let's say, like this. We found out that inverses were exactly symmetrical around this diagonal line, and that diagonal line is y equals x. And that's the reason why our algebraic techniques, the compositions have to be equal to x, because they're symmetrical around y equals x. That's why it's x. So that's neat. Thanks for watching this tutorial. We'll practice this in class. See ya.